so that they can evolve in tandem. But that's still ongoing.
Great. All right. Thank you again. We'll ask the next speaker to come up virtually, I suppose. This is David Chiang from University of Notre Dame. David, if you're ready, you can turn on your video.
Hi, thank you.
All right.
Okay, should I start?
Audible.
Hi, can you hear me?
Yes, you can go ahead. Yeah.
Hi, thanks. Thanks everyone for talk of the conference. My name is David on translating recursive probabilistic programs to factor graph grammars. This is joint work with Ken Chan from Indiana University, and the extended abstract for this paper is available at this URL here. So just by way of disclaimer, I just work on natural language processing. This is my first time attending, let alone presenting at a probabilistic programming conference. I'm still learning a lot about probabilistic programming languages, and maybe it will show a little bit, but I'm eager to see what questions come up. Okay, so in this talk, I'd like to talk about a very, very simple probabilistic programming language. And this is an example program in this probabilistic programming language that samples a random tree from a probabilistic context-free grammar from the full distribution, not for a fixed string. So it samples from the infinite set of trees generated by the PCFG. And there's not too much that's interesting about this language, except that it does allow recursion. And the recursion doesn't have any kind of restrictions like bounded recursion depth or limiting to iteration over sequences, or special cases like PCFGs. Even though this example is for PCFGs, it's not limited to that case. So it just lets you do recursion, and we want to be able to allow recursion and allow exact tractable inference. That's the goal. So the way we're going to do this is using a formalism that I've been developing with my student Darcy Riley called factor graph grammars, and these are presented. These are going to be presented at NeurIPS this year, and the URL for that paper is right here. And FGGs are based on a formalism that was developed in the late 1980s called hyperedge replacement graph grammars. And what they essentially are is they're context-free grammars for generating graphs, and we're using them for generating graphical models, factor graphs. And FGGs are expressive enough to subsume many other tractable formalisms, and they're also constrained enough to allow for finite variable domains, they're constrained enough to allow for exact and tractable inference. So the goal of this paper, so the NeurIPS paper talks about FGGs. The goal of this talk is to talk about how to translate this simple probabilistic programming language into an FGG. And the hope is to enable recursion on the programming language side and enable exact inference on the FGG side. So let me say a little bit about what factor graph grammars are. Like I said, they are essentially like context-free grammars, but for graphs. And so what we have here is we have a graph that's like in the process of being generated by an FGG. So we have the circles represent random variables, the small squares represent factors, and these squares with symbols inside them, these are non-terminal labeled hyperedges. And so these squares or hyperedges can be replaced by rules of the grammar. Okay, so this is only part of a factor graph, and these are the points at which the graph is continuing to grow. So on the right, we have some example FGG rules. So like CFG rules, they have a left-hand side and a right-hand side. And the meaning of this rule is basically wherever you see this pattern on the left-hand side, you can replace it with the right-hand side. The dark colored nodes are called external nodes, and they're kind of the anchor points that tell you how to stitch in the graph fragment when it replaces this non-terminal symbol here. Okay, and here we're going to be rewriting this D4 symbol here, and we can choose either one of these rules because they're the 4 is just an identifier. The actual non-terminal symbol is D, and so either one of these rules could apply to D4. So I'm going to show you an example of using this first rule, and I've just renumbered everything so that all the numbers are unique. And then the right-hand side of this rule will replace D4 like this. So now I have a larger partial factor graph, and you can see that there are now 3 non-terminal symbols available for rewriting, and this rewriting process will continue until there are no more non-terminal symbols. So because a non-terminal symbol can be rewritten in more than one way, we get a set of graphs, not a single graph, and in general, an FGG generates it can generate an infinite set of factor graphs. So, and the example that I just showed you does generate an infinite set, and these are just the first few of that infinity. So each factor graph describes a distribution over assignments to its random variables. So in FGG, because it describes a set of factor graphs, it describes the joint distribution over derivations of the FGG and assignments to the random variables that appear in that derivation. Okay, so you can think of the distribution described by an FGG as being the sum, or somehow some kind of composite of all of the distributions described by the individual graphs. All right, so as I said, the purpose of this talk is to talk about how to translate a program into one of these FGGs. And most of the rules of this translation are not that exciting. I'm going to show you the two kind of non-trivial cases. So the first one is conditionals, and the second one is functions. So for conditionals, here we have an example conditional expression. It's a mixture of Gaussians. Flip a coin. If it's heads, we sample from a Gaussian centered around 0. If it's tails, we sample from a Gaussian centered around 5, and that becomes 2 FGG rules. Most expressions just become a single FGG rule, but conditionals become 2 FGG rules. So if this expression is called E, then I make a non-terminal called E, and it can be rewritten in 2 ways, one for each branch of the conditional. So in the first branch, the coin flip is V1, and there's a factor that constrains V1 to be true. And in this case, V2 is a sample from a Gaussian with mean 0. The second rule constrains the coin flip to be false using this factor, and then it sets V2 to be a sample from the Gaussian with mean 5. Okay, so because either of these rules could apply, each derivation of the FGG corresponds to one branch of computation of the program. Okay, second case, functions. So this is a really, really simple example of a function call. It defines f to be the identity function and then just calls it on the number 42. So this first rule translates the function definition. So it just says wherever you have an f, you can replace it with this bit of factor graph that just says the return value is equal to the argument because f is the identity function. And this is what the function call looks like. If this says v1 is the constant 42 and then applies f to it. So one limitation of the programming language as it stands now is it does not have higher order functions. So functions can be recursive, mutually recursive, but they're just first order only. Okay, so here's a slightly more complicated example that combines both the two things that I just showed you. So this computes the factorial of 42. And so here's the function call. This again sets v1 to 42 and applies f to it. Now there are 2 possible rewrites for f because f has a conditional inside it. The first one is for the base case, and the second one is the more interesting one. And you can see that the right-hand side of this rule has another f non-terminal in it. So because f is a recursive function, it translates into a recursive rule. And in this particular case, the recursion depth is determined by the value of the argument that you pass to it. But in general, this condition here could have been depending on a random variable, and so there could be a non-zero probability of reaching any arbitrary recursion depth. So the full set of branches of computation of this program could be an infinite set. You have to have probability 1 of terminating, but there could be an infinite number of possible branches of computation. Okay, so how do we do inference in FGGs? So the full details are in the NeurIPS paper, and it describes several cases of inference, but the one I'd like to focus on is where all of the random variables are discrete and with finite support. And what happens here is if we want to compute the sum product, so this is the sum of the sum products of all the factor graphs generated by the FGG. If we want to compute that infinite sum over all the factor graphs, then the way we do this is we convert the FGG into a system of equations. And then we solve that system of equations. And one of the unknowns in the equation will be the desired sum product. And this is just kind of a cartoon diagram of how this works. We're going to compute the sum product of each left-hand side of the grammar and each right-hand side of the grammar. So the sum product of a left-hand side of the grammar is just the sum of the sum products of its possible right-hand sides. Okay, and then the sum product of the right-hand side, in turn, is computed as kind of as you'd expect. It's the sum of the product of the 3 things inside the right-hand side. So we sum over all possible assignments to the 3 random variables in here. We multiply the value of this factor, and then we multiply the sum product of D4, and then we multiply in the sum product of D5. Okay, so the left-hand sides depend on the right-hand sides, and the right-hand sides depend on the left-hand sides. If the grammar is recursive, then we can't just solve these equations by substituting. But well, okay, so if the FGG is not recursive, then we can solve it by substitution. That's the easiest and most common case. Familiar to people who've implemented CFGs or HMMs or things like that. But if there is recursion and each function has only one recursive call in any given branch of computation, then the system of equations will be linear, and we can use standard linear algebra methods to solve this system of equations, even if there's an infinite number of possible graphs. And this will be some kind of time, cubic time in the number of unknowns in the system of equations. If there are two or more recursive calls, then we cannot compute this exactly, but we can do successive approximations by Newton's method, and each method will take cubic time again, and the number of iterations will depend on the particular properties of the grammar. But the best case scenario is that Newton's method, I think, doubles the number of bits in the answer at each iteration. Okay, so what are the kinds of things that we want to use FGGs for? As I mentioned at the start, I work in natural language processing, and I'm interested in building natural language processing models. And one of the particular things I'm interested in is integrating finite automata of various kinds into neural networks. And this is something that's actually super common. It doesn't always go by that name, but it's extremely common to put a conditional random field, which is a kind of weighted automaton, as the output layer of a recurrent neural network. There's another kind of output layer called connectionist temporal classification, which is super standard in speech systems, and that also is at base a kind of weighted automaton. And these things are kind of tricky to implement, and there's plenty of shrink-wrapped libraries that will let you put one of these layers on an RNN. But what if you want to experiment with other kinds of automata? So for example, I have one student who's interested in doing the same thing, but the output layer is a push-down automaton instead. And this is quite tricky to implement, but the hope is that we could make implementing these sorts of things a lot easier if we had a programming language support for doing these kinds of things, like weighted or probabilistic automata, and being able to sum over all the paths through a non-deterministic automaton. So the same student, Brian Dussel, has a paper at this year's Connell using a slightly different setup where a recurrent neural network and a push-down automaton talk to each other. So the RNN passes probabilistic signals to the PDA, telling it whether to push or pop probabilistically, depending on its current state. And then the push-down automaton will send signals back to the RNN, telling it what's the probability distribution over its current top stack symbol. And the two work together to try to predict the next word of a sentence. And there's some pretty interesting results in here on modeling some non-deterministic context-free languages. Another one of my students, Justin De Benedetto, had a paper earlier this year at ICML. One piece of this paper was looking at a very, very popular neural network called the transformer. And there's a piece of the transformer called the positional encodings, which are kind of mysterious looking. And our paper reinterprets positional encodings as being computed by a weighted automaton. And so one natural question that would arise is, can we generalize this to other kinds of automata, especially if you want to build transformers for trees or graphs or other kind of structures? It would be natural to use tree automata or graph automata to compute the positional encodings for those things. And again, that can get quite complicated to implement, but with the proper programming language support, we hope it could become really easy. So for future work, none of this has been implemented yet, except, the translation that I've talked to you about is implemented, but all it does is it translates programs into the LaTeX figures for the paper. We need to actually implement something that actually works. And the lion's share of that implementation really is the implementation of FGGs themselves and their inference algorithms. And the actual translation should be quite simple indeed, but the implementation work for FGGs is all still future work. I'm also interested, I just leave you with this kind of curiosity. So this translation is not surjective. So every program in this little language can become an FGG, but there's plenty of FGGs that are not the translation of any program. And this is an example of the kind of thing that the translation would never produce. It's a function that has two inputs, V1 and V3, and it has two outputs, V2 and V4. And by itself, like a function with two return values is not that weird, but the FGG would be perfectly happy to make V3 depend on V2. So this is a function that conceptually, it's a function that you would enter twice or more times. And that feels like some kind of a coroutine or a generator or something like that. But I have not yet worked out what kind of change would we need to make to the programming language to expand the set of FGGs that the translation would generate. All right, so thank you very much for your attention. And again, thank you for staying to the end of the conference.
Let me see if I can turn my video on. Maybe I can. There I am. David, thank you for a fascinating talk.
Thank you.
There are a couple of questions. So the first question is, can you give an intuitive sense in this translation from probabilistic program to factor graph grammar, how kind of the randomness in the program factors into, I guess, what you could call the randomness of the derivation and the random variables in the factor graph once you've kind of sampled from the grammar, right?
Yeah, I think this is a great question. So there is this kind of two-level nature to FGGs that I think makes them really really flexible and kind of user-friendly. That I feel like they kind of combine like the graphical model way of looking at things and the kind of the more circuit way of looking at things, to reference an earlier talk from today. And there's some wiggle room there. So I'm not sure if I can give an intuitive sense, because there are cases where you can choose to put that randomness in the graphical model part, or you can choose to put the randomness into the derivation part. And so there's not always a definite line between the two, and it might depend on your taste or the application or something like that. There probably are cases where you have to do one or the other. If you have any kind of cycles, then the cycles need to go into the right-hand sides of rules, because the FGG derivations cannot be cyclic. They're always directed acyclic graphs. So that would be a constraint, where if you have anything that involves cycles, those would have to go into the rules.
So maybe
other than that, yes, go ahead.
Maybe I can ask
and anywhere where you have choice,
anywhere
where you have variables that wink into or out of existence, those would be in the derivation, and those would not be able to be in the, in the graphs. Yeah.
So maybe I didn't quite follow from the talk, and apologies if I didn't understand. But so does this mean that when you write a program, maybe actually you're going to have to annotate it in order to make it clear for the translation kind of what goes into the grammar and what goes into kind of the random variable?
Well, so the translation that I've just described, no, each program will become a unique FGG, and it doesn't require any annotations.
I see.
But as a practical matter, like when we actually implement this, you know, that sort of thing is imaginable for efficiency's sake, that maybe some kind of annotations would be necessary to maybe shift the burden from one to the other. Yeah, I can imagine that. Yeah,
I see. Yeah. Okay, then one more question from Vikash Mansinga, who also says, thank you for this kind of really interesting talk.
Yeah, thank you.
Are you here thinking about grounded language understanding applications? So maybe things similar to kind of the type of work that Stephanie Telex has been doing in kind of robotics?
I'm sorry, no, I have not thought about those kind of applications at all. And I know of Stephanie Telex, but I'm not familiar enough with their work to well, no, for sure, I'm not thinking of any applications along these lines, which is not to say that those things could not be thought of. I just haven't personally.
Okay, then one more technical question maybe. So in practice, how performant is the use of Newton's method here? How does it compare to kind of Monte Carlo approximations?
Great question. I'm sorry, I don't know. This is a super good question, and since I haven't implemented it, I don't know. Well, so the use of Newton's method to solve these equations is something that's been studied already quite a bit, and some of those papers do have experiments. So I'm not sure, but some of those papers could make some of the kinds of comparisons that are being asked here, but I myself have not done those comparisons, so I'm not sure. It's a great question. The one thing I can say is that Newton's method, you know, under suitable conditions, under pretty reasonable conditions, I think you'd have a stronger confidence that you're getting closer to the solution than with Monte Carlo methods, but maybe I'm wrong about that. I think there might be stronger guarantees about the convergence, but I'm sure other people here know better about that than me.
All right.